All right. Rest all the settings are good to go. Hit apply. Now we are going to create our bridge. So double click here to open up bridges and culverts data dialog box. This is the geometry that I extracted from the center line. Let's go ahead and let me show you the trick here. So first thing what I'll do is go to this geometry adjustment and I'll adjust my upstream face and the downstream face to the same horizontal station. That way, whatever changes which we make to my upstream face, I can simply copy it to downstream one. So in the geometry adjustment drop down, I'll choose shift stationing. I'll choose river reach intersection. Let's give it a reference station of 10,000 here. You can adjust upstream and downstream cross sections as well. Click on apply. Now you can see our upstream and downstream are centered on the same horizontal station. Now from here, things are very easy. You see these roadway geometry points that the software extracted from the underlying source. I'm going to remove that and I'm going to create my bridge opening now. I'll choose this remove roadway geometry point. Let's drag the selection box. This is a sloping deck bridge. I'll copy that to downstream now. Here you go. Let's build our bridge opening. From the drop down, I'll go to build bridge opening. Now I know for this bridge, the low chord elevation is 742. However, if you want, you can pick it from here as well, from the plot. Now I know the reference station has 10,000 here. Let's say the span width for bridge is 100 feet. And it also has piers, 2.5 feet diameter, 30 feet center to center spacing. Once done, copy that to downstream, click on build. We have a bridge opening created here. Now, this bridge, remember I told you this is a sloping deck, so you can see our high chord and low chords don't match. So let's go ahead and fix the low chord here. From the drop down, I'll go to deck roadway. The moment I select this point, you can see here, hang on, let's select this point. There you go. We are going to update this here. Let's change this elevation to 743.2. Now the deck is fine. I'll copy that to downstream cross section. Now I don't have to worry about measuring the elevation difference between the top of the pier and this low chord. We will fix these piers automatically using our bridge piers option, wherein I define any higher value of top of the pier elevation, let's say 800 feet, and the software will automatically trim the pier to match the slow chord. So I'll click on it, first enter, you can see it's fixed, copy to downstream. Even this pier is fixed, copy geometry to all our piers are fixed now. Now this is where you define your ineffective flow area. Remember, you need to define that. I'll choose to draw multiple ineffective flow areas. Click on draw here. Let me expand this tolic box and I can place my ineffective flow area. I don't have to be very precise here. I'll let the software do these work for me. So I'll roughly draw my ineffective flow areas. And I have this command that will match it with high chord. Click on fix overlapping. It cleans up these. So copy that to downstream. You have it all sorted. Then you define your methodology that you want to use. You can use your momentum and your nil. You can define your drag coefficient as well as the shape coefficient. Here, let's say it's circular pier. So using the lookup table, I am just defining that again. For the shape coefficient, let's say it's without diaphragm. Using this lookup table, I can define it. In case if you want to account for pressure and wear flow, you can choose this option. And once all of that is done, you're all sorted now. Click on close. The bridge is created right there. Take a look in 3D. There you have your bridge structure created. There you go. Similarly, in case of culverts, all you need to do is instead of defining your piers, you will just go ahead from the drop down and define your culvert. Go to this, you can remove all those bridge piers and you can simply create your culvert alignment. And you have to follow along the same steps for your dam as well. I'll provide you with one crisp short video, which will show you how to perform the dam break analysis as well. So you just have to follow these steps and you'll be able to create these kind of hydraulic structures in here. So with this, I'm going to wrap up my 1D model. Any questions from what you saw here? See how easily you could create your bridge structure. Similarly, you can create your culverts. Just to quickly show you here, let's say this was the existing condition of the model where you had a bridge. Now you are asked to remove this bridge opening and add a culvert there. So you would be creating a proposed scenario. In that case, you do not have to go ahead and set up your entire model from scratch. You will simply choose this duplicate current scenario and you will call this as, let's say, culvert or proposed condition, whatever you want, you can call that culvert. Hit apply. Let's close this. Now here we are now in the culvert scenario. This is my default. In the culvert scenario, let me quickly just show you how you can set up the culvert. From the drop, double click on this bridge opening, and here I'm going to get rid of these piers first. So go to bridge piers. I'll select all these piers, and I'm going to remove all of those from here. So you can simply choose to delete this piers which we have in the model. That's all gone now. All right. So once your piers are gone, you do not need this slow chord like this. So let's go ahead to my deck roadway and I'll remove my low chord elevation as well. Same, copy that to downstream. And here now I can include my culvert. From the drop down, I'll go to culverts and you can choose what shape of culvert you want here. And I'll go ahead with the circular one for now. And of course, then you can define your culvert alignment, your barrel placement and all this. So let's say I'm going to create one single barrel culvert. I'll place it here. So it picks your stationing for downstream and upstream and all. You can choose to define your diameter. You can pick that off the map view as well. Let's say this is the diameter. Let's round it up to 6 feet. And distance from the upstream face to the cross section, you mean this distance you have to measure. And once that is done, you have to provide your upstream invert elevation. Let's say this is where my culvert lies. For the downstream invert elevation, you would like to pick a positive slope for, let's say, I'll go ahead with 724. So I have a positive slope which the software computes for us. Then you define the Manning's value for top and bottom. Let's say this is a concrete culvert pipe barrel. It picks that up. And if any portion of your culvert is blocked, you can choose your depth blocked as well. So here, in this case, you now have culvert defined. There you go. So you have now a culvert alignment defined in here. So, and of course, in this 3D view, it if you make it larger, you might just see a pipe. So you have a culvert instead of your bridge now. Bridge opening, the piers are gone, you have this culvert defined. If you want to add more barrels, you can simply choose to place it another one here. Let's go ahead and do so. Let's put another one. That's it. Hang on. You have all these 3 barrels defined. You can see here. You can place this alignment. You can always change this alignment as well. So let me show you where. There you go. You have your culverts placed here. Click on close, and we have the 3-barrel culvert defined. So that's how easy it is. Similarly, you can draw your dams and all those structures as well. You need to have bounding sections. We'll make sure that you have those bounding cross sections for all those hydraulic structure which you have in the model. With that, I'm going to wrap up our 1D model. I'll move on to 2D. Let me know if you guys have any question before I do that. Any questions from what also? Hey, you guys, any questions?
You can move on, but if possible, you can like a side of the channel. You can add like one pond to see how it is simulated with different simulation elevations.
You want to see the results?
Oh no, you add first the pond, then you simulate to see if there is a change between, to see whether there is a difference before adding structures and after adding structure.
Meant pond. Hello.
Pond side of the channel.
Ah, okay, this
Mm.
one. Let's say if you want to add a storage area here, I'll show you what you can do that here. Go to storage area. You can draw it or you can assign it. Let me see if I can go ahead and assign it. So I can select this, go to storage area and choose assign storage area. It's selected, give it a name called pond. And that's how easy you can do that. Apply, close this. Now, first thing what you will do, right click and choose extract storage area volume curve. Here I don't have any elevation difference. Let me first go ahead and let's manipulate the terrain surface a bit. So this is what you have to follow. Hang on. Let's generate the color relief for our terrain surface. You can see here. Now I'm going to adjust the elevation here for my pond so that, there's some elevation, some storage available in this one. So I'll go to my terrain ribbon. I'll choose just elevation. You saw the elevation in this pond right now is 746. I'm going to reduce this by 10 feet. I'll choose just elevation command. Click on pick. I have the polyline alignment defined. Let me turn off my HEC-RAS layer once. I'll pick this one. Right click, choose done. And I'll choose an elevation offset of -10. So that will reduce that elevation by -10 here. And it's going to create a copy of my terrain surface and then modify it so that I don't lose out on my original data here. Let's call this adjusted DEM. Hit save. Click on adjust. Now this time you will see the elevation in my adjusted DEM would show me 10 feet less. Let's generate the color relief. Here, you can see it says 736. So as I hover my cursor on my DEM at any point, it will give you the elevation. It is now, take a look here. In the pond, it's 736. Initially, for my original terrain, it was 746. Now remember, you cannot just simply place your storage areas just like that in your model. There are rules. You have to define lateral structure to place the storage area to define the connection. I'm just giving you an idea. While you create your model, you go ahead and do that. So you have to have your lateral structures created if you place your ponds laterally. So you will create a pond, right click and choose extract storage area curve. Choose the right DEM and you can see here uh, just give me a quick second. Let's say 746. It won't adjust like that. I have to pick an outer boundary of this one. Yeah, it's inside, so let me remove this. And I'll draw one from the outside so that it captures the detail. I'm going to do that roughly. You need to be more precise when you are creating for your own model. Draw your pond. Once done, right click, choose done, give it a name called pond. Hit apply, close it. Now, if I choose right click, extract storage area volume curve, the software is going to automatically extract. So you can see we have 14 feet of elevation difference. Click on extract, and you can see it automatically extracts the storage capacity of the pond. Now, if you have storage area like this, you need to first draw your lateral structure. If you have storage areas on the lateral placement or you have on the side of the river, you need to connect it to your HEC-RAS model through lateral structure. If it's placed on the upstream or the downstream end of your model, you can simply move your river inside. That's it. In this case, you will have to draw your lateral structure. So let's go ahead and do so. Let's say this is where my lateral structure is placed. And you can choose. So now it gives you an option here. Where does the water from the river goes into? So you will choose adjacent SA2D flow area and you will choose the pond. That's it. Click on apply and the lateral structure has been created now. If you want to take a look at the connection, it will show you. So it now has your elevation information and all. You have your connection defined with the river reach. So that's how you will place it. And you in the boundary condition, if you have the storage area with certain elevation, you can go ahead and define that easily in here. You can define these boundary conditions for the model. Again. And here you can define the pond elevation. Let's say if it's dry, you can do that. If it's bank full elevation, you can simply choose the bank full elevation, which was 746, and you can define that here. Let's say for all the profile, you had it fill. So that's how you define your boundary conditions and all. Okay, was it clear now? Try it with your model so you will have much more clarity, okay? And here, if I go to help, go to this product tutorial, you have everything available in this case. So whatever we are covering here today, you have everything available. So don't worry if you forget anything or if you're not, this 1 hour session, 1.5 hour session, it can get really overwhelming. It's a lot of information. So don't worry, you have all these to help you out. So if you want to create the bridge, we followed along these steps, just watch the video. You have everything explained. Now you have complete training available for GeoHECRAS. And in case if you want to practice, you can download the same data set which I'm showing you. You can download that tutorial data set and you can practice so that you have an understanding on how to set up the model. In the first video itself, it will show you how to define your bridges and that storage area like we created and the lateral structures, everything's available here. Session number 11 is for your 2D model. And here the session number 8 would be your dam break simulation. And it's so easy to create in here and you can refer to these videos. So whatever we have covered today, you have everything available in here. So don't worry about missing out on anything. You can see you can easily create your dams and all. So same goes for
Excuse
your,
me.
yeah, any question?
Yes, a question.
Yeah,
So
go
if I
ahead.
caught you well, previously you said that you may not necessarily need the DTM for 1D. So, but I didn't catch well that point.
I'm so sorry, your voice is not clear. Can you repeat the question?
So previously you said that, so for 1D modeling, so you may not necessarily need the
Need a
DTM.
DEM. Yes, exactly.
Yeah. So I didn't catch well that point.
Oh, you didn't catch that. See what happens here in your 1D
Yeah, yeah.
model. In your 1D model, the cross sections are the real heroes of the model, okay? You need just the cross section data. That is now, if you can extract this data even from any other different sources. When we run the model here, let me show you, go to my plan, the scenarios. We don't have any terrain surface utilized here. These cross-section geometry, which you see here, these were extracted from the contours in my CAD file. Right now, I'll show you the difference, okay? If you
Okay.
have a DEM, it is perfect. Whenever you can generate the DEM, go ahead and do that. Whenever you can get DEM, go ahead and do that. It's going to help you more. You can create your 2D model and all that, but even without the terrain surface, you can run the model here. Let's take a look for this matter. Let's take a look at this particular cross section here. So these cross sections which we have in our model, we extracted these cross sections from our CAD file. Remember this? Here, when it talks about the extraction data, we used our CAD drawing and the contours in here to extract the geometry. Let's take a look. So you can see these points which you have here, these are all the intersection point with your contours. So you have limited points here. Now, if I were to extract this geometry even if I have a DEM, if I want to utilize that, go to extract geometry. This time I'll use elevation grid and use the DEM. Let's say this digital one, click on OK. And the geometry has been extracted. Now let's take a look. You will have much more points this time. There you go. You can see you have a lot of points now. From the drop down, if I go to geometry data, you will have more than 400 or 500. You will around something 500 points this time. Initially, you had just 10, 15 points. So now you can extract the geometry. So as long as you have your cross-section geometry data available, you would not need a DEM. If you've gotten your surveyed cross sections, let's say you have surveyed points for your cross section, you can go and create your cross sections directly using the survey data here. You can import it and you can run the model even without the terrain surface. Okay, you got the
Yeah, yeah,
point?
yeah. Yeah, I got it. I got it.
Perfect. Any other question?
Oh, that we can move on 2D so that we save time.
I'm sorry.
We can move on 2D so
Okay.
that we can have
Oh,
many sessions about 1D and 2D and the combination of them.
right now, let's go over to the 2D model. Give me a couple of seconds. I need to grab my bottle of water here. Hang on. Okay. All right. Now let's go ahead with the 2D model. So for the 2D model, I'm going to create a new scenario, a new plan within the same project itself in the flood study. So I'll go over to the scenario manager. Now click on new. I'll create a 2D model here, 2D flood study. Now 2D flood study is unsteady simulation. Remember that? And it works with mesh elements, so I have to create a new geometry file as well. And terrain surface is mandatory for our 2D model. So I'll use the same terrain that we generated right at the beginning of this session for this 2D model, and it's unsteady simulation. So I'll switch to unsteady. Let's rename this. All right. Now we are in the 2D flood study scenario. Let me turn everything else off. We don't need this. We don't need the shapefile layer group anymore. Let me turn that off. This is 2D. This was our culvert. This is our, of course, 1D flood study with bridge. You can easily create multiple scenarios, multiple plans within the same project, and you can switch between different scenarios. All right. Now, let's go ahead and create our 2D model here. Before I do that, we have these building structures in our model. These buildings are going to impact our flood analysis. So I want to bring these buildings into our model. Right click and choose add layers. And this time I'm going to bring in those buildings which have elevation attribute that we can utilize. So let's go to our consulting folder and let's bring in our buildings. We have a build shapefile here somewhere. Hang on. There you go. Click on open. You have these buildings now. If I click on it, it highlights. If I expand the data explorer, you can see these buildings now have an elevation attribute. Each of these buildings have their own elevation information. So if I select another one, you have different elevation. You choose this one, you have different elevation. So let's go ahead and utilize this information now. So I'll go over to the properties of this building shapefile layer here. And remember, those buildings which we were using previously did not have any elevation attributes. So we changed the offset above terrain to 25 feet to give it a 3D look. Now these buildings here have elevation attributes, so I can utilize that. From the drop down, I'll choose roof elef. That is my elevation attribute here. I'll extrude walls, use Mapler imagery, and of course, let's go ahead and change the transparency a bit, change the border stylization and the color fill. Once that is done, click on OK. Now buildings are all well defined. Now take a look in 3D here. You can go ahead and grab this 3D rotation tool and rotate the view around, and you can take a look at these buildings. These are all in 3D now. Each of these buildings have their own elevation and all. All right. Now, okay, let's switch back to 2D view. Now, rather than me having to digitize in the model domain and other elements to construct this 2D model, I'm going to bring in some files that will speed up this process here. So we'll go over to my map data layers panel, right click and choose add layers. And there are a few buildings which I want to bring in, a few shapefiles that I want to bring in. This model domain, riverbank, centerline, roadway, Woodward Creek. Now, when you select more than one shapefile, it creates a group for you, and you have all these model your shapefiles in the single group. Now, these shapefiles which you are seeing here, these shapefiles been directly created in GeoHECRAS itself. You don't have to go to any GIS tool to create these shapefiles. All you need to do is right click and choose new layer, and you can either create a drawing file or a GIS shapefile. If you choose to work with GIS shapefile, you can create either point shapefile, polygon shapefile, polyline shapefile. Let's say you want to create a polygon shapefile, you can even give it some attribute, you can choose a field type and all, and you can create these shapefiles right within the software. All right. Now, let's go ahead and define this 2D model extensor. So looking at this large polygon, the upper side is our downstream boundary. Now, this is where the flow exits the model domain. Whether the flow exits out along the entire boundary or just a portion, we do not care. This is called a flux boundary, and it just represents where the flow exits our model domain. Similarly, at the bottom of the screen, this is our flux boundary or the upstream boundary representing where the flow enters our model domain. And on the sides, we have these Akron Peninsula Road on the right, Riverview Road on the left. These are elevated roadway structures. And if you take a look in 3 as well, so we are going to model the valley area between these roadways. So I assume that water will not go out beyond these elevation here. So if in case water surface elevation rises beyond this bounding elevation, HEC-RAS will create a glass wall of water on the sides, which is called a slip boundary, and water will not be able to flow past that boundary. So whenever you're faced with a scenario where your water logs, accumulates on the sides of your 2D model, you will get an idea that water surface elevation is higher than this bounding elevation, and I need to extend my model domain further. So remember this, when you create your 2D model, always follow the high ground feature. And if in case your water surface elevation goes higher than this bounding elevation, we'll have to extend your model domain further. You can make use of this GIS tool here, reshape polygon. Let's pick this. Let's say if I have to reshape this polygon, I'll go ahead and easily do that. Let's say I have to extend this model domain further. So this is how it will look like. Click on OK. It will extend your model domain. There you go. I do not want these changes. Control Z, undo that. Now, 2D models are really simple, very precise, and you can create these 2D models easily. Once you're thorough with your project objective, once you have the necessary data requirements which you have for the model, once you have that all, whenever you can, go ahead with the 2D model. And do not unnecessarily complicate it with hybrid models. Hybrid models are not always your right solution. Prefer to do it either in 1D or in 2D. If you can create your 2D models for your project, go ahead and create your 2D model only. Anyway, let's go to our input ribbon. We can start assigning this information now. So if I go to my 2D flow area dropdown, you can see there's a command that will let you draw your 2D flow area directly. Now, if you have polygons, you can easily assign those. I'll choose assign command this time, click on pick. I have this polygon, I'll choose that as my 2D area. Once done, hit apply. Let's close this. I'll turn off this model domain shapefile layer, and you can see there's a slight color graduation change where my model domain was defined. And if I click on it, it highlights. If I double click on it, it opens up our 2D flow area data dialog box. Now, this dialog box has tools that will let you create and edit your 2D models here. In HEC-RAS, they have something called the uniform mesh, which is basically square elements. So if I define a cell size of, let's say, 100 feet here, and if I click on update button, which you see here, it's going to create a 2D mesh with 100 feet by 100 feet square cells. Hit update, it creates a 2D mesh with square cell elements of 100 feet by 100 feet. Let me show you a problem here. If I zoom into this roadway crossing, you can see there's a cell center right in the middle of this roadway here. Now, I do not know if you remember the theory on control volumes, but this right here, this is a cell of water, and water comes in and out through these faces, which is called flux. and the computation of the cell is handled at the cell center point. But the problem with this approach right here is that you can have water coming in from one side of the cell and magically appear on the other side when it is physically not possible due to this elevated roadway crossing which you have in between. But the software wouldn't know that. So this is where the concept of break lines come into picture. Break lines are a very important part of your 2D. This is a very integral and important part of your 2D model. You define break lines in areas where you have a break in your terrain surface and you need to align your cell elements accordingly. So your river portion, the overbanks, if you have wide river, the roadways in your model, make sure that you assign those as break lines. So whenever you have a break in your terrain surface in your area of concern, make sure that define your break lines properly and judiciously. So we are going to add some break lines to our mesh here. Let's close out of it. I'll turn off my HEC-RAS layer as well as the base map imagery. Let me turn off my color relief for this DEM. Now you can see we have these polylines here. These polylines I can utilize as my break lines. However, if you want, you can go ahead and draw your break lines on the fly as well. In case if you have lines already drawn, you can simply assign them. Click on pick like you do in AutoCAD, draw a selection box left to right. It selects all of these, right click and choose done. Selected all of those, it's going to auto name them, hit apply, let's close this. I don't need my shape files anymore, I'll turn it off now. The moment I turn on my HEC-RAS layer, you can see these break lines have been incorporated in my HEC-RAS here. Now, right now, it doesn't know what's happening here. It knows there's a break line, so we need to update our mesh so that our mesh elements are aligned themselves, they are aligning themselves with the break lines here. So double click on the 2D flow area to open up 2D flow area data dialog box. The moment I click on update, the software is going to recreate the mesh, and this time the flow will not be splitting across like it used to do earlier. You can see these cells are now aligning themselves with the roadway crossing and the rivers and all. So you make sure that you use your break lines in areas where you have a break in terrain surface, where you are analyzing your model, and judiciously define your break lines. Now this is what HEC-RAS does. Let me turn off the space map image to right click, choose zoom extend so you can see the entire model at once. Now, in your 2D model, let's say if you have any area of interest, you would like to define smaller cell size there to figure out or to study everything in detail there. So that the software captures everything in detail there. Now, when you're using this uniform mesh from HEC-RAS and you have any area of interest, you define finer cell size there, and using uniform mesh, you will end up with the same cell size throughout your model domain, regardless if you need them. And in case of your 2D models, remember your number of cells in your model, if it's too high, the computational time would be high. So more the number of cells in your model, more would be the computational time. Now, if you're dealing with a huge area with not much changes happening in the topography, it's fairly flat, you wouldn't need as much cells in your model. So we worked with two of our technical partners, Stantec and AECOM, and they assisted us in developing a more robust and efficient meshing scheme called the adaptive mesh. The moment I switch to this new meshing scheme, you can see I do not have to define any dimensions, and it will align the mesh element size in such a way that you have your gradually increasing cell size. It relaxes the mesh in areas where there is not much going on. And of course, it changes the mesh element size based upon the local area requirements. So when I click on update button, it's going to recreate the mesh. This time you'll see cell properties are much better, more uniform shaped where they need to be, and there is a gradual transition element size, and you end up with lot less mesh elements and much more computationally efficient mesh. So this is our adaptive mesh. The moment I click on close, you will see the map view updates with the new mesh here. Let me turn on the base map imagery, and now we are going to add our boundary condition lines and define our flow values. So I'll go over to my SA2D boundary condition element, click on draw here, and let's draw my downstream boundary first. I'll draw a polyline here, right click, choose done. Let's give it a name. Let's call this as DS for downstream. The moment I hit apply, you will see it would snap to the model domain here. Again, click on draw. We are going to draw our upstream boundary condition line. Right click, choose done, give it a name, called BCUS for upstream. Hit apply. Now we are ready to define the flow value and the boundary condition. So double click on the boundary condition line to open up the unsteady flow data dialog box here. Now for the downstream boundary, I'll go ahead with normal depth. Click on measure, it jumps to our boundary condition location. All you need to do is just draw a polyline representing the flow path, and the software will figure out the approximate energy slope for us. Right click, choose done. Now for the upstream boundary condition, I'll use a flow hydrograph. I have a time series data. Remember, your 2D model is unsteady simulation. You need a time series data here. I'll use a hydrograph. I have the hydrograph for this model. Click on define, and this is where I can define my boundary condition. I have the flow time series data here in my Excel sheet. I've copied it and I'll simply paste it here. Now this hydrograph is on a daytime interval of 15 minutes. Entire hydrograph is 24 hours long with a peak discharge of 14,000 CFS here. Again, we have to measure the energy slope. Click on measure. It jumps to our boundary condition location. Again, draw a polyline. Doesn't matter you draw it from upstream to downstream or downstream to upstream. The software will estimate the energy slope for us. There you go. Now, let's say my river is not dry initially, so I'll set some initial stage. Now, let me just close out of this. Let me place the bank full depth of here. We might see 728 is fine. So I'll use the bank full depth. Let's say my river is not dry. I'll provide it some initial stage of 728. All right. Now we are finally ready to run our 2D simulation. So see, that's how easy for you to set up your 2D model. Go to analysis, click on this little running person. It would want to know the start date and the end date of the simulation. I'll pick today's date as the starting date, tomorrow's date as the end date. I'll keep the computational time interval and the output interval as the default value here. Click on compute. First thing, it's going to convert the terrain surface into a format that HEC-RAS understands. Then it's going to run our 2D simulation. Once that is done, I'll show you the results. I'll show you the problem which you can encounter using your HEC-RAS and how GeoHECRAS overcomes those. Let it run, and once done, I'll show you. Let's go to results, go to flood map. This time you will have multiple options for your flood map. You have water surface elevation, your flood depth, velocity, depth times velocity square. These are hazard maps. And of course, a bunch of other ones in here. Let's go ahead and create a flood map for this flood depth. You can also create a raster grid for the selected flood map. Let's turn on the map view legend, click on OK. You'll see it's generating a flood map for us now. Let me turn off this layer for a better visibility. You have water initially, and you can change the animation speed, hit play, and you can see the flooding. And if you pay close attention here, you will see a problem that you can face with HEC-RAS here. Take a look at this building. The water continues to spread out, and it does not see any impact from these buildings whatsoever here. It continues to spread out. In fact, if I pause this animation, turn on the particle tracking, You can see these water particles are tracing through this building as if it does not even exist. Well, so this was a problem that AECOM brought to us, and they said that we need to develop additional features to get this fixed. So we worked with them, and we developed some additional HEC-RAS features in here. So let me just turn on this HEC-RAS layer, turn off my flood map, and of course, let's go to our input ribbon. Now, we developed additional features called 2D ineffective flow areas and 2D conveyance obstructions. The standard HEC-RAS does not have these, but because we are driving HEC-RAS through RAS controller, we were able to incorporate this into our model here. Let's go ahead and assign these buildings which we have in our model as our conveyance obstruction, 2D conveyance obstruction to be precise. These buildings are on the single shapefile layer. The software automatically selects that. These buildings have elevation attributes. Software selects that as well. Click on OK. Now these buildings have been marked as 2D conveyance obstruction. Now we need to update our mesh so that the software it computes the principal axis by looking at the major and minor axis of each of these buildings, and it's going to align the mesh elements accordingly. So right now you can see you have these buildings which are not enforced. So the moment I click on update, it's going to create a very detailed representation of the buildings with additional vetted perimeter and all that in the model now. You will have a very detailed boundary defined for your buildings and all. There you go. Now in our software, one more thing I would like to point out that we automatically fix the bad cell elements. Now bad cell elements are those elements which you have in which has more than 8 faces. So those are your bad cells. Those cells have more than 8 faces. It's not allowed in HEC-RAS unless you get rid of all your bad cell elements. You would not be able to run the simulation. So if I click on, if I uncheck this or fix bad elements, if I click on update, you will see some of the bad cell elements appear in the 2D mesh here. All right, you can say it says 16 of those. Now, in order to fix those, you need to go ahead and add a node and fix each of these cells individually. Rather than doing that, simply click on this auto fix, turn this on, click on update, let the software clean up the mesh for you. There you go, it's done now. We'll run the simulation once more. We'll see the impact from these buildings now. Go to analysis, click on the still running person, and it's running our 2D simulation once more. Less than 30 minutes into the 2D modeling, we are already running our second iteration for this 2D model. And also with HEC-RAS, you end up having to work with two separate programs. You have your normal HEC-RAS and you have your RAS mapper. Now the user interface for both these programs are different. The zoom and pan commands are different, and the menus are different. So it's kind of frustrating to work with. Whereas in our software, we drive everything through AutoCAD interface, so everything's really consistent in here. Okay, so now we have the simulation run done. Let's take a look at the results once more. Go to results, go to flood map. It's going to delete the previous one and regenerate the new one. Let's turn on the manipulation, click on OK. It's generating a flood map for us once again. Okay, let's turn this layer off. And this time you would see that our flood would honor the building as it should, and the water will go around the building as it should rather than going through it. Take a look. There you go. It honors the building this time. And if you want, you can pause this animation. You can turn on the particle tracking. And here, let's pause this, turn on the particle tracking, and you will see these water particles are now tracing around the building. Alrighty. Now you can turn off this particle tracking. You can also generate the velocity vectors. These are dynamic. If I zoom out, you will see less of those. There you go. and you have maximum minimum flood map, you'd be more interested in the maximum one. Once you have your maximum flood map created, you can export this out to CAD or to shapefile. And of course, you can export out this entire model out to these different software, which I've already talked about. And the last part of this, if you want to see the results at any given section, you will go to this profile plot drop down and you'll draw a profile line along the section where you want to analyze the results for. For example, say this here, click on apply, double click, and it opens up your profile plots. All right. So there you have the plot, which you can copy and paste it in your report. And then you have the same data defined in the tabular format, which you can export to Excel. You have different plots available. You can take a look at the water surface elevation, the velocity against terrain and all. You can easily do that. There you go. So with that, our session today here is done. Now, some of, I guess one of you mentioned about hybrid models. See, if not required, do not use hybrid models. And there are rules to define your hybrid models, wherein you can combine your 1D element with your 2D model. You have, again, set of rules that you need to follow. Now, in case if you have your river and cross sections define this area as your 1D model, overbanks as your 2D model, you will use, in that case, you will use your lateral structure to define the connections between your 1D model and 2D model, just as you did for your storage area. Now you can have your 2D model placed, let's switch to 1D first. Now let's say you can have your 2D model placed on the upstream side of it or on the downstream side of it. In that case, you need to define the last cross section at the border of your 2D model. Now, in this case, let's say if I want to define, hang on, let me just quickly duplicate this current scenario. I'll call this 1D, 2D. I'll copy the geometry and everything else here.
So excuse me.
Yeah.
Okay, for the first simulation, so I saw that the water was moving over the buildings. So how do you know that this is not the case of submergence? If the, for example, if the buildings are short, so for the case where the water can move, can
Yeah.
submerge the buildings.
In that case, see, if you're, in this case, these buildings had higher elevation, water did not cross it. In case if your water surface elevation goes higher, your buildings would be submerged. Now, there are another way for you to represent your buildings. What you can do, you can simply go ahead to your terrain ribbon and you can again use these adjust elevations to actually manipulate the topography there, okay? And in that case, you will have your terrain surface modified to represent the buildings. And if your water surface elevation goes higher than the building, it will go above that building structure. Although that's not the natural case scenario, you might not face such scenarios. But in case if you have to do that, you would simply use this adjust elevation command, and you can just use the topography with modified buildings in here. You can simply, for example, I think, did you see the part where I adjusted the elevation for the storage area? I used negative offset of 10 feet. And for example, if this area I want to go ahead and use this as buildings, I want to stamp this building in my terrain. For example, here you can take a look. So this was another building. Now, if water surface elevation reaches the level higher than this one, it will cross it. And what you can do in this case is you have to define, now you, in your 2D model, in order to define the specially varying Manning's value, you have to go ahead and create a land cover layer. Remember, in this case, you have to create your land cover for 2D models, and you can define a higher Manning's value. So you have ways to represent buildings in your model. Most of the time, you will simply assign them as your 2D conveyance obstruction, or if you want, you can go ahead and modify the topography of the model, or you can define it as an area with very high Manning's roughness. There are three ways you can define. See, now the idea for this session was to make you familiar with the modeling, and now for your project, start your model. I'm going to share this link with you. Go to this products tutorial right within the software. And once you are in this tutorial video, let me share this link with you. All of you make use of this link. I'm dropping it in the chat box. Follow these videos. Follow the steps that are covered that I showed you today. If in case you do not remember this, when you create your own model, follow these tutorial videos and create your model. If you face any issues with that, you can always reach out to us for help, okay? Create your model. If you face any issues, reach out to us and we will help you out. Okay?
Yeah, yes, okay.